6.4 Graphs of logarithms. Very similar to the graphs of exponential section. This falls into the category of it's going to be shorter than the textbook because I'm going to assume you've seen these transformations at this point 3 times, I want to say, maybe even 4. So if that section didn't make sense, if this section is continuing to not make sense, definitely go back and go to the transformation section. I go through how to do every reflection, stretch, shrink, translation with much simpler functions in that section. Now, to kind of really hammer home the connection between the two. When we talked about an exponential, the exponential domain of an exponential is always negative infinity to infinity. The range of an exponential, unless it's been transformed, is 0 to infinity. Well, a logarithm is, you just flip those. So the domain in this case will be 0 to infinity, and the range will now become negative infinity to infinity. So if we're trying to find the domain of a logarithm, we kind of use a process. So when we talked about domain a while back, I mentioned at the time that there's 3 types of things we'll see in this course. There is a fraction, and there's a process to find the domain of a fraction. There is square roots or roots, and there's a process to find the domain when given a square root. And then there was, quote unquote, pretty much everything else, where this is the time that this breaks that pretty much everything else. That's not to say forget that whole process, because it still holds entirely true, but we just have to add kind of one little additional thing to the everything else section. And so that's logarithms. Logarithms do have their own domain. When we get into solving logarithms, we need to be checking our answers again, because we can have extraneous solutions. But as far as the process goes, it's the exact same process as a square root. It's just, instead of greater than or equal to 0, it's just greater than 0. So that's why I'm saying the method still works, the 3-type breakdown still works. It's just, when you see a logarithm, think, okay, it's square root, and now it's just greater than 0 versus greater than or equal to 0. So to see exactly what that means, we have this logarithm. We take whatever is inside. I don't care what the base is. I take whatever is inside, x minus 4. I'm going to set it greater than 0. And then I just go ahead and solve. Add 4 to both sides. So my domain is 4 to infinity. Now, as far as kind of just a very brief introduction of logarithms, the graph on the left is not a logarithm at all. It's an exponential. We've seen that before. What a logarithm is, and this is how you graph any inverse. We've talked about this before, I believe. Yeah. Is we draw a y is equal to x line, kind of a dotted line that's not even really there, and we flip it over that line. So the graph on the right, again, the top thing is still my exponential, but the bottom thing in blue or maybe purple, depending on how you look at it, that is my logarithm, and that's because it's an inverse. And if you look at that graph, oh, okay, yeah, the domain is 0 to infinity, the range is negative infinity to infinity, and we're going to talk about some other properties. But that's where this comes from. If you had never seen a logarithm before, you wouldn't really even need to know specifically what a graph looks like, because there is this relationship. And that's where the shape is kind of coming from. Okay, yeah. And so when we talked about exponentials, the parent function standardly, but not always, or typically, was y is equal to 2 to the x. And in this case, unless otherwise specified, generally we talk about the parent function of a logarithm to be log base 2 of x. And so that's what the blue graph is. Now to talk about kind of all the properties, just like we talked about them when we were dealing with an exponential. If I have a function y equals log base b of x, my vertical asymptote is going to be x is equal to 0, which makes sense because my domain is 0 to infinity. My range will be negative infinity to infinity. My x-intercept is going to be 1, 0, and this would be true of regardless of what your base is. So b could be 3000. Your x-intercept is still going to be 1, 0, and that feeds into, or that comes from kind of the fact that we ended the last lecture with log base anything with 1 on the inside will always get you a result 0. And another property, again discussed in the last lecture, is if those bases match up, your output will be 1. So the other key point we deal with logarithms is always whatever your base is, comma 1. And yes, I think up to this point, every parent function we've seen has 2 or 3 key points. This one's only going to have 2 because you start to get really weird functions from there. But you could figure out another one by just plugging in a point. Really weird values, not functions. And then your y-intercept is going to be none unless you transform your graph a little bit, because, I mean, that makes sense. Your x, or your vertical asymptotes, x is equal to 0, so there should be nothing crossing your y-axis. This is the graph. The top one is if your b is greater than 1, and the bottom one is if your b is between 0 and 1, just like we had with exponentials. One is going to kind of have that arcing curve to the right, going up, and the other one's going to have that arcing curve going down to the right. So if we're going to graph, seems kind of terrifying. We just learned about logarithms, and this seems like a bunch of weird numbers flying around in this question. I should have said y is equal to 3 minus ln of x minus 4. I apologize for that. Maybe I fix it in the next line. Nope, I do not. But that's fine. We have the properties. We're going to write down our key points. We're going to write down our transformations because we've seen all of these transformations before. We're going to apply them. We're going to plot points, and we're going to graph. So yeah, seems like a lot, but it's something we've done twice, if not 3 times before. So the key points are going to be, well, 1, 0 is always going to be your key point regardless of what the base is. And then your other one is whatever your base is, and then comma 1. So we know ln is log base e, so my other key point is e comma 1. Now you might be thinking, okay, Zach keeps talking about this e, it's not really a value. No, it still is, and when we get to actually plotting our point, we'll talk about strictly what the value is. But for now, just imagine it's a placeholder and still just go through your process as though it was just any other transformation question. So the next step in the process of a transformation question is to describe the transformations. So looking at my 3 minus ln of x minus 4, my first transformation is I'm shifted to the right 4. That's what's inside my log. And then my second transformation is the negative outside means I'm flipping over the x-axis. So that means I'll be multiplying my y by negative 1. And then my last transformation is up 3. So now we apply them. First one is moving to the right 4, so I'm going to add 4 to both of my x values. My first point will become 5, 0, and my second point, like again, you could probably put this as a decimal if you wanted to, but for now let's just leave it as e plus 4, comma 1. And then my next transformation is reflect over the x-axis, so I'm going to multiply my y values by negative 1. So my first point is actually not going to change. It makes sense. 0 times negative 1, 0. And then my second point is going to become e plus 4, comma, negative 1. Last transformation is up 3, so I'm going to add 3 to both of my y values. My first point is 5, comma 3. My second point is e plus 4, comma 2. My vertical asymptote is not at, originally is at x is equal to 0. Okay, yeah. So my vertical asymptote for my parent function is at x is equal to 0, but now it is being shifted to the right 4. And so if you don't really even see that with the shift, you could still kind of go back to when we found the domain and realize that x has to be greater than 4. So now my vertical asymptote has shifted to the right 4, so instead of it being x is equal to 1, it becomes x is equal to 4. Instead of it being x is equal to 0, it has become x is equal to 4. And now we're going to put all of our pieces together in a graph. So my first thing that's easy to plot is x is equal to 4. That's just a vertical line. I drew it as a dashed line, which is kind of typical when we're dealing with asymptotes. Then 5, 3 is certainly doable to see. I plot it on 5, go up to 3. Something that is worth mentioning is the grid on this is a little bit weird. So they aren't spaced by 1s, they're spaced by 1/2. So my red line's on 4. My next line to the right is 6, or my next bolded line is 6. And so in between those is 5. So that's where that purple dot is showing up. And then I have to plot e plus 4 plus 2, or e plus 4 comma 2. So my horizontal line right there is y is equal to 2, And then now we're finally going to have to evaluate what E is. E, like I mentioned, is 2.7 something. So it's 2.7 something plus 4. I would definitely throw it in a calculator if I was you, which becomes 6.2 something. Or 6 point. So now we're going to put all of our pieces together in graph. So I'm going to plot my vertical asymptotes at x is equal to 4. It's that dashed line. I'm going to plot 5, 3. It's worth mentioning my grid's a little bit strange on the graph that we're seeing. So it's actually going up. Each box represents 1/2 versus 1. So right between 4 and 6 is 5. And then 3 is going to be, it's actually going to be 6 tick marks up from the bottom. And then my black dot is E plus 4, 2. And this is one of them. If you were sketching by hand, you would have to use a calculator or something. It ends up being, if you add E to 4, you end up getting 6.7 something. And then at 2, which is that bolded line horizontally. And so then we know, okay, we're dealing with a log function, and log functions are either going to kind of start from the bottom and swoop to the top, or stop from the top and swoop right to the bottom. And since this is being reflected, it is going to start from the top and swoop bottom to the right, which makes sense the way the points are lined up as well. So I would just draw a line that goes through those 2 points, make sure that I don't cross my vertical asymptote, and that is my graph. Now, if we want to go the other direction, and this is kind of how I ended the exponential graphing as well, we can either describe an equation to you, or we can give you a graph and make you translate it from the graph. So in this case, we have the graph, and I want to write a logarithm equation that will model this graph. So we kind of have to identify our pieces of information. And again, the grid's a little bit strange with this, but the vertical asymptote is at -3. And I have some points. My point is at -2, -1, and at 1, 2. With that information, I know at least that my graph has been shifted to the left 3. So I can say, okay, I don't know overall what my logarithm function is going to look like. I'm going to say I'm going to choose my base as just log base 10, because that's the easiest to deal with. And then I'm going to say, okay, I know that shifted left 3, so I have log x plus 3. I don't know what I'm multiplying that by. I don't know if I'm being shifted up or down, anything like that. So I'm going to kind of just put placeholders in there until I figure out what's happening. I think what probably would happen in WebWorks is they're going to tell you what base to use, but if they don't tell you which base to use, I would recommend using log base 10. So now we're going to plug in some values to figure out what these missing variables are. So I'm going to plug in my first key point, -2, -1, -2 for x, -1 for y, and then I'm going to simplify from there. So then my -2 plus 3 gets me 1. We know that log base, or not log base, log with an input of 1 is always just 0, so that actually goes away, which is nice, because now we have k. K is equal to -1. So I solved for one of those variables in that kind of the middle equation or the slide in the equation in the middle of the slide. And now we want to find my a. So I plug in my k, and I plug in my point now, the other key point, 1, 2. So my x becomes 1, my y becomes 2, and then again, now I'm going to be solving for a as opposed to k. I go about solving for a. So I add 1 to both sides. I divide both sides by log base, or not log base. I divide by both sides by log 4. And so that's it. I could round that if I wanted to. Like, I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. And so that's it. I could round that if I wanted to. Like, I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. And so that's it. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. And so that's it. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 over log 4. But I don't want to. I could get a decimal of 3 But why do extra work if you don't have to? So this is a perfectly fine way to write out this equation. Y is equal to, your A is now 3 over log 4 times log of x plus 3 minus 1. There's a lot of stuff going on in this slide. This, I would be very surprised if I saw anything like this on a test. You'll probably see 1 or 2 questions like this in WebWork. So it is worth maybe washing over one more time, but it is definitely not worth kind of losing sleep and making sure you can tediously understand each individual step. That's it for this section.